Today we'll go over the lab calculations for the experiment atomic emission spectra. The lab that you did today in class, let's review briefly what happened there. You had a power supply right here with a hydrogen tube in it, and you stood 1 meter away, which is 100 centimeters. And then your partner moved a pen or pencil on another meter stick to find out how far away the image was, and you would record the distance of that image, which was your X value for each color. When you did hydrogen, you should have found 3 colors. You should have found red. You should have found some sort of teal, green, blue, whatever you wrote down. And then you should have also had some sort of violet. It's okay if you had them in a different order, but you should have gotten your X values for each and your Y values for each. Your Y values are all going to be 100 centimeters because you were always 1 meter away. And these are the 3 data pieces that you should have recorded. So I'm going to give you some sample data on my part. I'm going to write 55.0 centimeters as my X. Remember that X is the distance between the tube and the line that your partner marked on the meter stick. So my X is 55 centimeters, my Y is 100 centimeters. And in order to find Z, you need the Pythagorean Theorem. So Z squared equals X squared plus Y squared. So I'm going to put my X squared is 55.0 centimeters. My Y is 100 centimeters squared. And then, of course, I'm going to have to square root that whole side to get Z. And when I calculate my Z, I'm going to get 114 centimeters with 3 sig figs. So that's my Z, 114 centimeters. So, of course, you're doing this with your calculations. And let's just do red. Now you're going to need to find the wavelength. The wavelength is equal to D times X over Z. So we already know X, we already know Z, but now we have to get this D. D is the space between the grooves in the diffraction grating. Now the diffraction grating had 750 grooves per millimeter. But what you want to do is you want to find the space between the grooves. So what you have to do is you have to inverse this and find out that you have 1 millimeter per 750 grooves. So when you do that math, you're going to get an answer of 0.00133 millimeters per groove. So the diffraction gradient, remember, has these tiny little ridges that you can't see with your eye. And these ridges, when light hits it, it makes the light split up into different directions because each one has a different wavelength. So the red might go there, the teal might go there, the violet's going to go there, and you're going to break it up into different directions and different distances from the tube. So let's do our formula now. The wavelength for me is going to be the D, which everyone's going to have the same D, 0.00133. Now be careful with your units. That's millimeters per groove. And then you're going to need your X. My X was 55.0 centimeters. And then my Z, what I calculated above, is 114 centimeters. And look at units. Centimeters and centimeters are going to cancel out, and you're going to have millimeters. However, you don't want millimeters. You actually want meters for these. So you're going to have to get this into meters. So you're going to do another conversion. We're going to get rid of millimeters and go to meters. There are 1,000 millimeters in a meter. So when you do that whole math, I'm going to calculate my wavelength of red to be 6.42 times 10 to the minus 7th meters. That is my wavelength of red, which is pretty close to what the wavelength of red is in real life. Now we're going to find the frequency. So as you recall, to find the frequency, we'll do the speed of light. So speed of light equals wavelength times frequency. So 3 times 10 to the 8th meters per second equals the wavelength you just found, 6.42 times 10 to the minus 7th meters. times the frequency which you solve for that. And my frequency comes out to be 4.68 times 10 to the 14th 1 over seconds. Or you could write s to the minus 1, or you could write hertz. Either one of those is fine. Now the reason we wanted the frequency is so that we can find the energy, which we'll do coming up soon. So let's first find the percent error of our wavelength. Well, my wavelength came out to be 6.42 10 to the minus 7. That's my experimental. 6.42 times 10 to the minus 7th meters. And the accepted value is 6.50 times 10 to the minus 7th meters divided by the right value, which is 6.50 times 10 to the minus 7th meters. And then that absolute value times 100. You can actually just totally get rid of that 10 to the minus 7th. You could factor it out of everything. So if I do 6.5 minus 6.42 and divide that by 6.5 and times 100, that will give me about a 1.23% error, which of course is not too bad. Hopefully you are close to a 0% error in yours. But if not, it is what it is. Okay, back to number 5. Number 5 here, we're trying to find the energy of the wave, so we need to use the frequency. My frequency I got for number 3 was 4.68 10 to the 14th. So energy equals h times frequency. 4.68 times 10 to the 14th, 1 over seconds. Planck's constant is always going to be 6.626 times 10 to the minus 34th joules times seconds. Notice that 1 over seconds and seconds cancels out. So my joules is going to be 3.10 10 to the minus 19th. 3.10 10 to the minus 19th joules. And that is for one little wave. One little wave. But if I want to get this for Avogadro's number of waves, I have to multiply this by 6.02 times 10 to the 23rd. And when I get that, I will do this. 3.1 times 10 to the minus 34 times 6.02 times 10 to the 23rd is going to give you 1.86 times 10 to the minus 1.87. 1.87 times 10 to the minus 10th joules. All right, now the last part is part B. You need to find out where this transition matches in energy change. So what you do is you go back to your notes and you make a chart just like this where you have all the energies of level 6, 5, 4, 3, 2, 1, and we did this with the formula. Remember to have the right values here as I have written on your screen right now. And what we're going to do is we're going to find out between which two levels this color changes in this much energy. So if you look at my energy level 3 and 2, it's going to make sense that if you subtract these two numbers from 3 to 2, it actually comes out to be very close to the energy that I got for my red light. So if I go back to my notes and I do, well, let me just do it on here. If I do 2.42 times 10 to the minus 19th minus, you can just do absolute value of all this, 5.445 times 10 to the minus 19th, you're going to get an answer of 3.03 10 to the minus 19th. So if I write that on my paper, you'll see that for 3 to 2, you're going to have 2.42 times 10 to the minus 19th minus 5.445 times 10 to the minus 19th, which equals 3.025 times 10 to the minus 19th joules, which is very, very close to that value you got over there. So that shows you that this transition was indeed from 3 to 2. Your job is to figure out which other transitions are for the teal and the violet.